Hi, so today we are going to learn toroid. A toroid produces magnetic field. It gives uniform magnetic field which is used in many devices. We know that a current carrying conductor behaves like a magnet as it deflects a compass needle placed in its vicinity. You will find that compass needle is deflected. So current carrying conductor is a magnet, a kind of magnet. Now when coils of several turn is made out of a current carrying conductor, then its magnetic field increases manifold. Here we have strong magnetic field which is comparative to magnetic field of a bar magnet. And this device is called a solenoid. Here we have a solenoid. Now when the two ends of this solenoid is joined together, we get this kind of structure. And this is called toroid. This is your toroid. So, there is several circular turns of coils of this current carrying conductor. Current is getting in and finally the current is getting out, and the shape is similar to a handball. If you compare the shape of this toroid with a handball. This toroid is a three-dimensional figure. Now we are interested to find magnetic field due to this toroid. So we cut a transverse section of toroid. It is your two-dimensional, figure. This toroid, you can see this toroid. I have cut a transverse section of this three-dimensional figure and we get a two-dimensional figure. Now you can see that if current is coming out from here, it can be shown by a dot, and current going in can be shown by a cross. So here I have drawn so many dots. Current is getting out from the surface, and here the current is getting in the surface. So direction of current is from top to inside at each and every turn. And we are interested to find magnetic field due to this toroid. We can see that there is a symmetry in the shape of toroid, and in this kind of situation, Ampere's circuital law goes well. So we will be using Ampere's circuital law. Shape of a toroid is symmetrical. And for Ampere's circuital law, first work is to draw Ampérian lobe. Step 1. Is to draw Ampérian lobe. So you can see that shape of this toroid is circular kind of. So we will be taking an Ampérian lobe which also is a circle. So three kind of Ampérian lobe can be obtained. An Ampérian lobe which is totally encircling the toroid. Now second kind of Ampérian lobe can be taken totally inside the vacant space of toroid. And third kind of Ampérian lobe can be taken inside the toroid. So one by one we will be discussing the magnetic field using Ampérian circuital lobe. So let us draw a circular Ampérian lobe enclosing whole toroid. With radius R1. Now at point P1 let us take a small length element dl. This length element is a vector quantity. So, using Ampere's circuital law, that is your line integral of B dot dl, this must be equal to mu naught and total current enclosed in the Ampérian lobe, I net. Now here you can see that at one lobe out of n lobes, so let me assume it, let there be n turns of circular lobe. Number of turns is n, capital N, and at each turn you can see that current is coming out at this very place and it is going inside. So at the top the direction of current can be taken along outside direction, this direction, and direction of current at the inner side can be taken in this way. The two currents are opposite to each other. So net current in one lobe is equal to I minus I, and this is equal to 0. Therefore, net current in n lobes is equal to n into 0. This also is equal to 0 only. Therefore, B dot dl, if you integrate dl length element, then total sum of dl length element will be 2 pi r1. But B is a constant. We know that at equal distances from the wire, B remains constant. So B will be constant everywhere at the circumference of the circle, which is at equidistance from the wires. So B is a constant. Now dl is integrated to 2 pi r1 and this is equal to 0. Since r1 is not equal to 0, it implies that B outside is equal to 0. So filled outside a toroid is equal to 0. Now we will find fill inside a toroid in the vacant space. Case number 2. Magnetic fill inside the vacant space of a toroid at point P2 at distance R1, R2. Can be obtained using the same Ampere's circuital law, and the law is line integral of B dot dl is equal to mu naught times total current flowing inside I net. Now we can see no current is flowing inside this Amperian loop. All the current is flowing outside the Amperian loop. Therefore, here I net is equal to 0. Now again, dl length element is not equal. Here dl cannot be equal to 0. Length element cannot be 0. It implies that vector B only is equal to 0 inside this Amperian loop, inside this toroid at vacant space. So we found that B inside the toroid in vacant space is 0 and B also is 0 in outside the toroid. Now let us take an Amperian loop going totally inside the toroid. So case 3. An Amperian loop passing inside the toroid. With radius r. Now let us select a length element dl at point P. And we will find magnetic field B at point P using Amperian circuital loop. Since we know that a line integral of B dot dl is equal to mu naught times total current flowing inside I net. Here you can see that inside Amperian loop you can easily see that the current is getting inside, and there are end loops. So if I current is there getting inside this open surface, then total number of loops is your n, and therefore I net is equal to n into I. Here you have line integral, and at equal distances we know that magnetic field B is a constant because B depends on R and R is a constant, so B is a constant. Now when you integrate dl length element, it will be equal to total circumference 2 pi r, and this is equal to n terms times I. Therefore B is equal to number of turns per unit length into I. Okay, here I have left mu naught times this much. Therefore B is equal to mu naught times small n I. Here small n is equal to number of turns per unit length. So this is the magnetic field B inside a toroid, here inside, and this B is a constant. You can see that mu naught is a constant, number of turns per unit length is a constant, and I also is a constant. So therefore B inside a toroid is uniform, constant. Now this toroid and solenoid are jointly used at many places. A combination of solenoid and toroid is used in a synchrotron. Synchrotron is actually an inclined cyclotron which is used to energize charged particle to a very high energy. It increases the velocity of a charged particle, so its energy is increased. Energy of charged particle is increased. Now there is one more device that is called magnetic confinement or magnetic bottle. A magnetic bottle is a device to contain very highly heated substances. We contain substances in some bottles, in some containers, but if the substance is very heated and is having temperature 2000 degrees C, 4000 degrees C, or even more, so such substances cannot be contained even in any metallic container. Those substances are contained in magnetic bottle or magnetic confinement. A magnetic bottle consists of two coils, coil 1 and coil 2. These are actually solenoid. So we have two solenoids at the two ends, and you can see that field lines are going away from each other. when field lines come out from the solenoid, here you can see it is going apart from each other. At the second solenoid also the same happens. Here you have south pole of solenoid, so the field lines are getting in. And here the field lines are getting out. Now let us learn the technique how the heated materials is confined in this region when we have not any kind of confinement, any container. It is there only magnetic field lines. So recall the Lorentz force. Lorentz force is equal to QV cross B. So suppose this material tries to come out from this very place with velocity V. Here the magnetic field is directed along tangent of magnetic field line. So if you take cross product of V and B, taking V the first vector, the magnetic force will be acting downward. So when the object tries to come outside, it is forced to go inside only. The same scheme can be considered at other places too. Here I take one point, and if this material tries to go out from this very point with velocity V, when there is magnetic field along the direction of field line, so V cross B at this very point can be only inside. So wherever you take one point and you find the velocity vector and B vector, then you will find the force vector is pointing inside only. And in this way you find that the heated material, any substance, is confined in magnetic field only. So this is a kind of magnetic bottle. In place of two solenoids, we use toroid also. A toroid is used in tokamak. So I conclude